Hello everyone. In this video, I'm going to discuss solution of some conceptual questions. So here is question number 1. It says a charge particle. This charge particle, which is a relativistic particle, it has velocity 0.6 c, which is close to velocity of light. It enters into this uniform electric field. So question is, as it moves in the electric field, its x component of velocity and x component of momentum, how they will change. So options say that x component of velocity remains constant or x component of momentum remains constant. This is a somewhat tricky question. If you apply Newton's laws of motion, assuming that mass is constant, then you will get wrong answer. So actually, in this case, velocity is high, so mass will change with velocity. Okay, so as the particle moves, its velocity is going to change, so mass will also change. So therefore, to solve this question, we will have to write Newton's equation of motion in this form: F equal to dp by dt. Okay, so if you write F equal to ma, then you will get wrong answer because this formula will not apply here. Okay, so F equal to dp by dt. See here, as the charge particle enters into the electric field, at some instant of time, it will be here. So force on the charge particle will be in the direction of electric field. So force is in x direction. Sorry, force is in y direction. So we can say that x component of force is 0 here. If x component of force is 0, so therefore we'll say that dpx by dt is 0 actually. So this implies that px is constant. Okay. Now px can be written as m into vx, which is constant. So therefore m can be written as m naught divided by root under 1 minus v square by c square, and vx, that is some constant. Let's say it is k. Okay. So therefore vx is equal to k divided by m naught and multiplied by 1 minus v square by c square. See here, as the charge particle moves at some instant of time, its speed is v. This v must be greater than 0.6 c. Okay, because of the presence of electric field, charge particle will definitely accelerate. Its velocity in y direction is increasing. Okay, so therefore, its net velocity is increasing actually. So v is increasing here. V is increasing. So if v increases, then this term actually decreases. Okay, and if this term decreases, then vx decreases. So answer is vx will decrease. So therefore, correct options will be vx decreases. Okay, this vx decreases and px remains constant. So these two are the correct answers. Okay. Now let's move to second question. It says a point charge q is placed at a distance 2r from an uncharged isolated conducting sphere. So calculate force on point charge q. See, this is point charge q and this sphere doesn't have any charge. Its charge is 0. Let's say q dash is 0. So if you think naively, it appears as if since it doesn't have any charge, so therefore force on this charge should be 0. But actually, case is not so. Force on this point charge will not be equal to 0. Reason is that because of the presence of this charge, some charges will get induced on the sphere. Okay, so this side will become negatively charged and this side will become positively charged. Okay, see, and negatively charged are nearer to this charge q, so therefore a net attractive force will act on point charge q. Okay, situation is something like this. Let me show you. So, see here, some negative charges will get induced here, and some positive charges will get induced here. So since negative charges are nearer, so net attractive force on charge q will act. Okay. So to solve this question, we will have to use image method. Okay. So here I'm giving you solution. So let us see, this is the sphere and the charge q is here. This distance is d, which is equal to 2r here. Its radius is capital R. So first of all, we'll put an image charge here, q primed at some distance x. So we know that q primed is actually equal to minus q into, sorry, this charge is capital Q. So capital Q into R divided by D. So D is 2R here. So if you put 2R here, you will get here minus Q by 2. So value of image charge will be equal to minus Q by 2. And its distance from here, from center of sphere, X will be equal to R square by D. So therefore, R and when you put D equal to 2R, you get here 2. So it is R by 2. So image charge will be at a distance R by 2 from here, from center, and its value will be minus Q by 2. Okay. Now, since this sphere was neutral actually in the beginning. Okay, a total charge on the sphere is 0. So to make total charge 0, we have to take another charge equal to image charge but opposite in sign. So image charge is minus q by 2. So we'll have to take a charge q by 2 at center. Okay, so that total charge on the sphere becomes 0. Okay, so therefore situation is something like this. Let me erase this. So situation is something like this here. We are taking image charge here minus q by 2, and here there is charge q by 2. So total charge on sphere is 0. So now this point charge q will experience force because of this minus q by 2 and plus q by 2. Okay, so therefore if you want to calculate force on this, okay, force will be something like this. Force because of q by 2 will be equal to k q by 2 and q divided by, here to here distance is 2r, so this is 2r whole square, and force because of this minus q by 2 will be k q by 2 and q. See, since this force will be toward leftward and force because of this will be rightward, so that's why I'm subtracting the two. And distance from here to here, this x is actually r by 2 and this was 2r, so distance from here to here will be actually 3r by 2. So therefore here we write 3r by 2 whole square. Okay, so let's take common term outside. So kq square by 2 and divided by r square, these are common terms. So here we get 1 by 4 minus, here we get 4 by 9. Okay, so that's what we have. So therefore answer will be minus 16 minus 9. So minus 7 aq square and divided by 72 r square. That is the force. Okay. So that is the force because on this point charge because of this uncharged sphere. So situation initially was something like this. There was uncharged sphere, and in front of this there is a point charge q. Its distance from here was 2r, and this is r, and this radius is r. See, this is ungrounded. Okay, if this sphere were grounded, okay, in that case this q by 2 won't be there because grounded sphere. Uh, when a grounded sphere is there and a point charge is kept in front of it, then sphere develops a net negative charge which is equal to value of image charge. So in that case we need to consider only this minus q by 2, but to make it neutral we are putting another charge q by 2 here. Okay, so that is the answer to this question. Now let's move to third question. Says suppose magnetic charge is discovered. We know that magnetic charge doesn't exist presently, but question says suppose magnetic charge is discovered, write expression for electromagnetic force on a particle which has electric charge q and magnetic charge qm due to electromagnetic fields. See, so we are talking about a solution. We are talking about a particle which has charge q and magnetic charge qm, and it is moving in an electric field E and magnetic field B. You know, such particle which has both electric charge and magnetic charge, such particles are called dions. Okay, so let's say this is a dion, and we want to know what is the force on this dion because of electric field and magnetic field. We know that if there is a particle which has charge q, then force on this charge is simply q e plus v cross b. So this is the electric force and magnetic force. Okay, so this is electric force and this one is the magnetic force. But now we have to add something here. Okay, because now this particle has another property which is magnetic charge. So because of the presence of magnetic charge, there will arise some other term here. Okay, so that term we have to think of. Okay, so what that term is. So what I'm going to do is, first of all, let us write Maxwell's equation after magnetic monopole is discovered. See, Maxwell equation we write like this: del dot E is equal to rho by epsilon naught, and del dot B is equal to 0. Third equation is del cross E is equal to minus del B by del T, and fourth equation is del cross B is equal to mu naught J and plus epsilon naught del E by del T. These are Maxwell's equations. See, these equations are true when no magnetic monopole exists or magnetic charge doesn't exist. Okay, this equation actually implies that magnetic monopole does not exist. So now if these equations are true when magnetic charge is zero. Okay, magnetic monopole does not exist. Now if magnetic monopole exists, in that case, if QM is not zero, in that case Maxwell's equations modify like this: del dot E becomes rho by epsilon naught. So now here we write rho E so that we understand this is electric charge density. Okay. Now here there is del dot B is equal to, in analogy with this equation, we write here rho M and we multiply by mu naught. This just balances the dimension. Okay. So rho M, this factor is to balance the dimension. Okay. So del dot B is equal to mu naught into rho M. Now third equation becomes del cross E is equal to minus, here we write mu naught and Jm and minus del B by del T. This is the this is what third equation becomes. Okay. And fourth equation remains as it is. Del cross B is equal to mu naught and J and plus epsilon naught and del E by del T. The fourth equation remains the same. See, in third equation, we write here negative sign because if we don't write negative sign, then we won't get correct equation of continuity for magnetic current. Okay. See, this will be called magnetic charge density and this will be called magnetic current density. Okay. So if we do not write negative sign here, we will not get correct equation of continuity if we take divergence here. See, if you take divergence here, you will obtain correct equation of continuity for magnetic charge and magnetic current. Okay. So to ensure that we get correct equation of continuity, we put negative sign here. Okay. So now you see here, after Maxwell's equations are rewritten in this form, okay, uh, it looks somewhat symmetric. Okay, it becomes a somewhat symmetric equation. See here, if you just change E, if you replace E by B, okay, in this equation and rho E by rho M, then first equation transforms into second equation. Similarly, here if you replace E by B and Jm by, suppose you replace E by B and Jm by minus Je, suppose let us call it Je, electric minus Je, and B by minus E. Okay, then this minus and this minus becomes plus and you obtain this equation, and extra factors we can balance are used actually to balance the dimension, so that we can always take care of. Okay. So now we can say here that, see, there is a transformation. We can convert electric field into magnetic field. Okay, we can convert Je into Jm. Okay, or we can convert rho E into rho M, or we can do the reverse. Okay, you can convert B into minus E. Okay, see, we convert B into minus E. Minus E. See, if you want to convert B into minus E and rho M into minus rho E and Jm into minus Je. Okay, so we do transformation like this. Okay, so if you do this kind of transformation, one set of equation transforms into another set of equation. Okay, see here, if you write B equal minus E, okay, and Je becomes Jm, Je becomes Jm, and E becomes B, then obviously there will arise a negative sign from here, and so we will get these negative signs. Okay, so this kind of transformation has to be done if you want to transform one set of equation into another set of equation. Okay, so therefore now using this analogy, now we can write here magnetic force. So here I'm removing this question mark. See, there was charge Q, so I'm replacing electric charge by magnetic charge here, Qm. You'll replace electric field by magnetic field, and plus there is a term V, but now we are replacing B. There is a B, so B will be replaced by E. Okay, so B will be replaced by minus E. So here you will replace V minus E. We'll replace B by minus E, so we'll get V cross E. But to balance dimension, we'll write here C square. Okay, so if magnetic charge is discovered, then expression for electromagnetic force will become this. Okay. Okay, so this conclusion comes from Maxwell's equation. So, when magnetic charge discovered, okay, then these Maxwell's equation have to be rewritten in this form, and in this form, you can see that one set of equation transforms into another set of equation. Okay, if you do this kind of transformation, B E changes to B, or JE changes to JM, rho E changes to rho M. But if you do reverse transformation, B, then you have to replace B by minus E. Okay, or rho M by minus rho E, or JM by minus JE. Okay. So let's move to another question. Okay. It says a long wire which lies along. Okay, so therefore, final answer for electromagnetic force after discovery of dions. Okay, or the particles which carry both electric and magnetic charges. This will be the expression for electromagnetic force. Okay. Now let's move to another question. It says a long wire which carries long wire which lies along z-axis carries a current I. Calculate B dot dl from A002 root 3 a comma 0 along any arbitrary path. Okay, see, situation is something like this. The x-axis, this is y-axis, this is a point. Suppose this is a comma 0 and this is some point a comma root 3a comma a comma 0. So, and there is a long wire, there is a long wire here. It is carrying a current in this direction. So because of this long wire, some magnetic field develop around the wire. So in presence of that magnetic field, we have to calculate line integration of magnetic field from this point to this point, and path can be some any arbitrary path. Okay, path is not specified. It can be like this. Sorry, it can be any path from here to here. Okay, so path is not specified. So let's do the calculation. See, B dot dl we can write as it is. B can be written as mu naught I upon 2 pi r and phi cap, because long wire is along z-axis. If you put your thumb like this, magnetic field lines are circular, so circular and turning anti-clockwise. So therefore, we can say that magnetic field is along phi cap. Okay. Now dl, see, this path is on xy plane, so dl on xy plane can be written like this: dr r cap plus r d phi and phi cap. Okay, in xy plane we can write like this. So let's do dot product. This dot product will be 0, phi dot phi will become 1. Okay, and R will cancel out. So you get here mu naught I upon 2 pi and integration. See, R and R cancel out. So we get integration pi. So let's say from phi 1 to phi 2. Okay, mu naught I upon 2 pi. And here we get simply phi 2 minus phi 1. Okay, so phi 2 is basically polar angle at first position, and second position, and phi 1 is polar angle at first position. So here at, if you calculate it in this position, phi 1 will be equal to 0. It is on x-axis. And here if you calculate, see this line, and if you connect it like this, okay, so it is, see, this distance is root 3a and this distance is a. So this angle is phi 2 actually. Okay, so phi 2, if you calculate phi 2, it will be tan inverse y by x. Okay, for this point. Okay, so tan inverse y is a and x is root 3a. So we get here tan inverse 1 by root 3. So that is actually equal to pi by 6. So therefore, pi 2 is pi by 6, mu naught I upon 2 pi. And this is pi by 6 minus 0. So therefore, we get mu naught I upon pi cancel out, and you get here 12. That's the answer. Okay. The line integration of magnetic field from this initial point to this final point is equal to this much, mu naught I upon 12. Okay. Now moving to another question, question number 5. It says a sphere of radius r has uniform volume charge density rho. Calculate average value of electric field in hemispherical part of a sphere. See, this is a sphere and it has uniform volume charge density rho. Now, suppose this is the hemispherical part of the sphere. Okay, we have to calculate electric field average inside this sphere. Okay, its radius is capital R, let's say. We know that we have to calculate average of electric field inside the sphere. So we know that electric field inside the sphere is given by rho r by 3 epsilon naught. That is electric field inside the sphere. This is a very well known result, which is obtained using Gauss's law. Okay. Now we have to calculate average value of electric field. So we can calculate like this: E integrated over volume and divided by volume of this portion, hemisphere. Okay. So let's put the value rho r by 3 epsilon naught. So rho and epsilon 3 epsilon naught will come outside, and we will get here r vector d tau and divide by volume. See, r vector d tau divided by volume is nothing but center of mass of hemisphere. Okay, so if you take this as origin, okay, center of mass, we know that center of mass of this hemisphere lies at a distance of 3 r by 8. So therefore, this answer, E average, this is nothing but 3 r by 8. Okay, so we can write like this: E average modulus is equal to rho divided by 3 epsilon naught, and this is the center. This represents the center of mass. Okay, so this is 3 r by 8. Okay, so answer is rho 3 and 3 cancel out. So we get here rho r divided by 8 epsilon naught. That's the answer. That is the magnitude of average value of electric field in the hemispherical portion of the given sphere. Okay. Now question number 6. It says two cables of conductivity sigma 1 and sigma 2 are connected end to end and carry equal current I as shown in figure. So calculate charge at the junction. So here at the junction, we have to calculate charge. What charge is there? Okay. Okay. So let's write Ohm's law. See, we know that J equal to sigma E, where sigma is conductivity. So J can be written as current divided by area. Okay. So here, so current is I and area of cross section is A. All right. And here conductivity is sigma 1, and in this portion, suppose electric field is E1. So therefore, E1 we can calculate as I divided by A into sigma 1. Here sigma 1 is actually conductivity. Now, similarly, we can calculate E2, electric field in the second wire. That will be equal to current is same, cross section area is same, only conductivity is different. So we'll get electric field in the second wire to be equal to I divided by A into sigma 2. Okay. Now, so we have this kind of situation. Here, there is wire, there is junction. Here, electric field is E1. Here, electric field is E2, and there is some charge here. So let's say charge density is capital sigma. Okay. So we know that whenever we cross a junction or interface, electric field is discontinuous by an amount sigma by epsilon naught. So here we have E2 minus E1 is equal to charge density upon epsilon naught. Okay. Here, this capital sigma is charge density. Charge density. Okay. So we'll write now here I upon, let's put the value of E2 and E1. So if you put E2, you will get 1 I by A common, and you get here sigma 1 by epsilon 2, sorry, sigma 2, and here you get 1 by sigma 1, and this is capital sigma and divide by epsilon naught. Okay. So let's do the cross multiplication. Here we get I into epsilon naught, and here 1 by sigma 2 minus 1 by sigma 1, and here you get sigma into area. So sigma into area actually gives you charge. This is charge density. This is charge. I'm writing it as charge density. Okay. So this is charge. So I into epsilon naught and 1 by sigma 2 minus 1 by sigma 1. That is the charge at the junction. That's the answer. Okay. This was question number 6. Now move to another question. See, it says a spherical capacitor shown in figure is shown in figure. Radius of outer sphere is fixed. This radius is fixed, but radius of inner sphere can be varied. The maximum electric field that can exist near the inner sphere is E naught. For what value of R1 by R will the capacitor store maximum energy? So what should be the value of R1 by R so that sphere can store maximum energy? And it is given that maximum electric field near the surface of inner sphere is E naught actually. So electric field cannot exceed that value. So if electric field exceeds that value, maybe there will occur some breakdown. Okay. All right. So now So obviously, it will store maximum energy when this electric field becomes maximum. We can say that we put maximum charge. So suppose let's say that Q is the maximum charge. Okay. So if we put maximum charge Q here, we'll get maximum electric field near the inner sphere, which will be equal to E naught, and E naught will be equal to KQ divided by R square, R1 square. So therefore, from here we conclude that Q will be equal to E naught or into R1 square and divide by K. Let's call it equation number 1. Now let's calculate energy. So electric field at some arbitrary point R will be equal to KQ divided by R square. So you can calculate energy stored in capacitor as 1 by 2 epsilon naught and E square and d tau. Okay. So U is equal to 1 by 2 epsilon naught, and let's put the value of E. This is KQ by R square. This is whole square, and d tau will be equal to 4 pi R square and dr. Okay. Because there is spherical symmetry, so integration on theta and phi gives us 4 pi R square. 4 pi actually. Okay. So volume element directly have written 4 pi R square dr because theta and phi integration gives us 4 pi. Okay. Now integration will be from R1 to R, because if you put charge some charge Q here, field outside will be 0, field here is 0, only field in this region is non-zero. So energy is stored in this region only. Okay. So let's see what we get. Here you see 4 pi and epsilon naught gives you 1 by k. So that cancels 1k here. Okay. So you get here Q square upon 2. There is 2. And 1k will also be there. Okay. And this integration, see, r power 4 cancels out with r square. You get here dr by r square. Limit is from r1 to r. So now k and q we had calculated here. Q is this much. So we'll write here E naught r1 square and divide by k whole square. And this integration gives us 1 by r1 minus 1 by r. Okay, that's what we have. So now energy we have calculated, this is equal to, let's multiply by R1 power 4 this side. So we get here K, 1K cancels out. So you get here E naught square and divide by K. And there was a factor of 2 also here. Yeah, so there was factor of 2. So we get here 2. And when you multiply by R1 power 4, you get here R1 cube, and minus here you get R1 to the power 4 or divide by R. So that is U. This is the electrostatic energy. Now we want U to be maximum. So we'll write du by d R1, because R1 can be varied, equal to 0. So when you differentiate it, see this E naught square upon 2k is outside. And this differentiation, see, we are applying the condition of extrema. So when you do differentiation, you get here 3 R1 square and minus 4 R1 cube and divide by R. So from here you can calculate. Okay, you can calculate from here. See, r square term, r1 square term will cancel out. So from here we get r1 by r is equal to 3 by 4. That's the answer. So we were to calculate r1 by r. So we have gotten that value, which is equal to 3 by 4. Okay. So let's move to question number 8. It says a dielectric sphere which has dielectric constant basically epsilon r is placed in uniform electric field E naught as shown in figure. So there is some external electric field E naught in which a uniform dielectric sphere has been placed. So calculate force on right half of the sphere due to E naught. So due to external electric field, we have to calculate force on this dielectric sphere, sorry, half portion of dielectric sphere. See, this right half. Force on this right half we have to calculate, okay? So that's the question here. So what we will do is, first of all, we'll calculate charge induced on this right half surface. Okay. So for that, what we are going to do is we'll calculate net electric field inside dielectric, which will be equal to electric field applied and plus field appearing because of polarization. So this sphere will get polarized because of the presence of this external electric field. And we know that when a sphere gets uniformly polarized, it develops an electric field minus P upon 3 epsilon naught. Okay. So that is net electric field inside. This E is net electric field inside the dielectric sphere. Okay. And P is the field appearing because of polarization, which is well known to be minus P by 3 epsilon naught. Okay. So we'll write here like this: E naught and minus P. P is polarization, so polarization vector, which can be written as epsilon naught and chi E and electric field inside the dielectric, and divide by 3 epsilon naught. So that is, we know this relation for linear dielectric: epsilon naught, chi E, and electric field. So we are assuming this dielectric to be linear. So we are using it. Okay. Now epsilon naught will cancel out. You can take E to this side and take E common. So we'll get here 1 plus chi E and divide by 3. That is equal to E naught. So from here we get E to be equal to, okay, E to be equal to 3 E naught, 3 E naught and divided by 3 plus chi E. That is the electric field. So therefore, let's put this electric field into this equation. We'll get polarization vector is equal to epsilon naught chi E. And when you put this here, we get 3 epsilon naught chi E and E naught and divided by 3 plus chi E, which is the polarization vector developed. Okay. So now that is the polarization vector. So we can calculate bound charge densities developed on the sphere. Sigma B, which is equal to, sorry, sigma B is equal to P dot n cap. So here, see, polarization is in this direction. This is the direction of polarization. Okay. And at some point, you take n cap like this. Suppose this is at angle theta. So if you do dot product, you will get magnitude of P, and magnitude of n cap is 1 and cos of angle between the two. So this will just become P into 1 into cos theta. Okay. So sigma B is this. So let's put the value of P. So P is 3 epsilon naught and chi E and E naught and divide by 3 plus chi E and cos theta. Okay. So that's the sigma B. So let's calculate bound charge density, bound charge on half sphere. So bound charge will be equal to sigma B and ds integration. Okay, that is the bound charge. Okay. So integration is on hemisphere. So let's so sigma B and ds, if you write, it is r square sine theta d theta and d phi. D phi integration. So let's write d phi. Okay. So this is a double integration, sigma B. So we can put these things here. So we'll get here, let us write it as some alpha and cos theta. Later on, in place of alpha, I'll write all these things. Okay. So here we'll get alpha and r is this r square term will come outside, and we'll get here cos theta and sine theta and d theta, and there is d phi term also. Okay. So when you do integration of hemisphere, limit is 0 to pi. Okay. Theta limit is from 0 to pi by 2, and phi limit is 0 to 2 pi. So this gives 2 pi, and this integration will give you 1 by 2. Okay, you can check it. It will give you 1 by 2. So 1 by 2 and 2 pi. So basically you get pi from here. So answer is alpha into pi r square. Okay, so you can put the value of alpha from here. This was alpha. So answer is 3 epsilon naught and chi e and e naught. And ultimately this r square term is there. And obviously there is pi also. So you can write pi at the end. And divided by this 3 plus chi. 3 plus chi. So that is the force. Okay. So if we write here some clarity, force is force that we have calculated, magnitude of the force is, this is 3 pi epsilon naught and chi e and e naught and r square and divided by 3 plus chi e. If you want, you can put chi e to be equal to epsilon r minus 1. Okay. So this can be finally expressed in terms of that epsilon r which was given in the question. Okay. So therefore answer will become equal to, if you write in terms of epsilon r, this will become 3 pi epsilon naught and r square, this term, and e naught. And here you get epsilon r minus 1 and divided by, here if you write epsilon r minus 1, you will get epsilon r plus 2. So that is the force on half of the sphere. Okay. Because of the external electric field. Okay. The question was clearly written: force on right half of sphere due to E naught. Okay. This is not the net force on half of the sphere, okay? Because this half of the sphere will also experience force because of charges developed on this side. So that is not the net force, okay? Now, question number 9, it says a circular ring of radius A is kept in a uniform perpendicular magnetic field B naught, as shown in figure. So this is a ring of radius A. It is kept in a magnetic field B naught. For t greater than 0, field is decreased at a constant rate B. So here actually we have dB by dt is equal to minus B. So at some instant of time, dB is minus B into dt. Let's integrate. So at time 0, magnetic field was B naught. So at some time, magnetic field is B. Okay, at some time t. So we'll get from here B is equal to some B naught minus BT. So at some instant of time, magnetic field is this. Okay. Now this magnetic field is being varied, so some EMF will develop here. So EMF, if you calculate, that will be equal to d phi b by dt. That is area is pi into a square, and this will become magnetic field derivative because we are differentiating flux. So that's what we have. So dv by dt is b here. So this is pi a square and b. So that is the EMF. If you calculate induced current is pi a square b or divided by resistance. Okay, resistance. Okay, resistance is not mentioned, but we'll assume that resistance is R. Okay, so we have written this is induced current. We have calculated EMF. From EMF, we have calculated the induced current. We are assuming it to be resistive loop. Okay, so now question says if the wire can be a maximum tension T naught, after then after what time will the loop break? कितनी देर के बाद loop break हो जाएगा, ठीक है? So see what will actually happen here. See here magnetic field is decreasing, so flux is decreasing. Okay, so according to Lenz's law, the loop will try to induced current will try to increase the flux. Okay, so that can happen if area of the loop, see magnetic field is decreasing actually, so flux can be increased by increasing the area. So this loop will try to expand actually, so because of which some tension will develop. Okay, so let's calculate tension. So to calculate tension, let us consider half of the wire. Okay, so if you consider half of the wire, okay, here and here tension will act in this direction. Okay, here magnetic field is decreasing, so here current will get induced in the same direction, okay, as the magnetic field. So this is the direction of current. This is induced current, I induced. This is induced current. Okay, now induced current is in this direction, so you can calculate force on any element using this formula I dl cross b. Okay, so I dl cross b. So dl current is in this direction, b is in a downward direction. Okay, so if you calculate dl cross b, if you do if you curl your finger, you will find that force is radially outward on any element. Df is radially outward. Okay, so actually if you integrate it on, so you will get here force on any portion of the wire, okay, I, and it will become L cross B. Because B is uniform, it is not varying in space. So if you do integration, you will get integration on DL only. So you will get IL cross B. So IL cross B basically means if you take wire of any shape, what actually matters is only end to end distance. So this is first end and this is second end. So this will be called L actually. This is L. Okay. So this is L and magnetic field is downward. Okay, so you take L in this L is in this direction. Suppose we call it X direction and this is Y direction. So we can write here I, and L will be 2A I cap, and magnetic field is some B and minus K cap. So I cross K is minus A and minus plus. So you will get here 2I A B and J cap. So net force is in this direction on this semicircular wire. So we have considered semicircular for our convenience, okay, to calculate tension, okay, because if you want to calculate tension, you cannot consider whole of the wire because net force on the wire will come out to be 0, okay. So whole of the ring you cannot consider, okay. So to calculate tension, either you consider a small element. If we consider only a small element, then also we can calculate tension, but that calculation is somewhat complicated, okay. So to make it simple, we have considered half of the ring, okay. We can also consider quarter ring. By using quarter ring also we can calculate force. or tension. So if this wire is in equilibrium, upward force must be equal to downward force. So we have this kind of situation, F is equal to 2T, but F we have calculated, that is equal to 2I A into B. Okay, 2I A into B, and that is equal to 2T. So 2 and 2 will cancel out. So, and this is the maximum tension suppose we have reached. So tension will become equal to 2T naught at the time of breaking. So 2 and 2 will cancel out. We can put the value of I from here. I is pi A square and B and divided by R. This is resistance. And here again there is A and B we can put from here. See, B was equal to B naught and minus BT. That is equal to T naught. So now do some cross multiplication and obtain time from here. Okay, so if you do cross multiplication, you get here T naught into R. So we get something like this: B naught minus BT is equal to T naught multiplied by R and divided by, we are getting here pi B into A cube. These terms, pi B and these A cube. So from here we can, sorry, this was T, time. So time we are getting to be equal to, this term can be taken to this side. So B naught minus T naught into R and divided by pi B and A cube and divided by 1 by B. So that is the time. So after this much time, the loop will break if you keep on decreasing the magnetic field at this constant rate itself. Okay. Now, question number 10. It says if an electron is assumed to be a sphere and its radius, rest mass, energy is assumed to be only only of electric nature, then estimate radius of its electron. So we are assuming electron to be a tiny sphere. Its charge is E. Its radius is suppose something R. Then we know that electrostatic energy is equal to, for such a sphere, it is 3kq square upon 5r. And question says that rest mass energy, which is m naught c square, is only because of this electrostatic energy. So we can write this as 3kq square upon 5r here. So therefore, r will become equal to 3kq square upon 5 m naught e square. Okay. So let's put the values. 3 k is 9 into 10 to the power 9, and q for electron is 1.6 into 10 power minus 19. Okay. And this is 5. And so here I have put everything in a SI unit. Okay. And this one is m naught c square. We know that this is 0.5 mega electron volt, mega electron volt, 0.51 per electron, actually mega electron volt. This is in joule meter. Its unit will be joule meter because radius we are calculating. See, this kq square by r has unit of energy. So this is joule. So if we multiply it by r, then it will be joule meter. So this is joule meter. Okay. Now to convert joule into electron volt, you can divide it by 1.6 into 10 power minus 19. So one factor will cancel out. So you'll get here electron volt, and one this power will become 1. Okay, so electron volt will cancel out and you will get answer in meter. So finally, if you divide it by, see, we know that to convert joule into electron volt, we divide it by 1.6 into 10 power minus 19. Okay, so we can write 1 joule is equal to 1 by 1.6 into 10 to the power minus 19 electron volt. Okay, so therefore this factor will cancel out and electron volt will also cancel out. So you will get here 27 into 10 to the power 9 into 1.6 into 10 power minus 19. Okay, this is meter will remain here. Okay, and here we get 5 into 0.51 and mega is 10 power 6 actually. Yeah, electron volt got cancelled. Okay, so if you do this calculation, you will get answer of the order of 10 power minus 15 meter, which is actually of the order of radius of nucleus. Okay, so therefore we are not getting a correct answer. So therefore conclusion is that the rest mass energy of electron cannot be only of electrical nature. Okay, So in the beginning, initially it was thought to be of this kind, okay, but later on it was realized that if you do calculation in this way, you are not getting correct radius of electron, because electron is very tiny particle. Its radius is even something of the order of 10 power minus 40, or even less than this, okay. But it is here, the answer that we are getting here is of the order of radius of nucleus, okay. So definitely this is not correct radius, okay. So energy of rest mass energy of electron cannot be of electrical nature, okay. So this is all in this video, okay. If you have any comment, you can share with us, okay. I'm just writing down number here. So if you have any query, you can contact on this number, okay. So I'll be discussing some more questions in other videos.